He showed us how to think about difficult problems of quantum field theory in a simple, intuitive way. Almost everyone else was using another, older method to analyze the problems he was addressing. The older method was harder, but he had found a trick that made it all easy. The parton trick. Feynman waved his magic wand and all the answers popped out. Ironically, the older method was based on the Feynman diagrams. The best part of the lecture for me was when T.D. Lee interrupted to ask a question, or more likely to make a statement disguised as a question. Feynman had claimed that a certain kind of diagram never occurred in his new method, and that simplified things. It was called a Z-diagram. Lee asked, "Isn't it true that in some theories with vector and spinor fields, Z-diagrams don't always give zero, but I believe it can probably be fixed up?" The lecture hall was silent as a crypt. Feynman looked at the Mandarin for 5 seconds, then said, "Fix it." Then he went on. After the lecture, Feynman came over to me and asked, "Hey, what's your name?" He said that he had thought about my question and wanted to talk about it. Did I know a place where we could meet later? That's how we wound up at the West End Cafe. We'll come back to the cafe, but first I need to fill you in on some additional points about gravity and quantum mechanics. The question that I wanted to discuss had to do with the effects of quantum mechanics on black holes. The general theory of relativity is a classical theory of gravity. When a physicist uses the term classical, he doesn't mean that it comes from ancient Greece. It just means that the theory does not include the effects of quantum mechanics. Very little was understood about how quantum theory would influence the gravitational field, but what little was known had to do with small disturbances that propagate through space as gravitational waves. Feynman had contributed most of what we knew about the quantum theory of these disturbances. In Chapter 4, we learned that God apparently ignored Einstein about playing dice. The point, of course, is that things that are certain in classical physics become uncertain in quantum physics. Quantum mechanics never tells us what will happen. It tells us the probability that this or that will happen. When exactly a radioactive atom will decay is unpredictable, but quantum mechanics can tell us that it will probably decay in the next 10 seconds. The Nobel Prize-winning physicist Murray Gell-Mann borrowed this slogan from T.H. White's The Once and Future King. Everything not forbidden is compulsory. In particular, there are many events in classical physics that just cannot happen. In most cases, however, the same events are possible in quantum theory. Instead of being impossible, these events are just very improbable. But no matter how improbable, if you wait long enough, they will eventually happen. Thus, everything not forbidden is compulsory. A good example is a phenomenon called tunneling. Imagine a car parked on a hill with a dip in it. Let's ignore all irrelevant things such as friction and air resistance. Let's also assume that the driver left the handbrake off so that the car is free to roll. It's clear that if the car is parked at the bottom of the dip, it won't suddenly start to move. Motion in either direction would involve going uphill, and if the car is initially at rest, it won't have the energy to move uphill. If we later found the car rolling down the hill beyond the hump, we would assume that either someone had pushed it, or it had gotten the energy to go over the hump in some other way. Spontaneously jumping over the hump would be impossible in classical mechanics. But remember, everything not forbidden is compulsory. If the car was quantum mechanical, as all cars really are, nothing would prevent it from suddenly appearing on the other side of the hump. That might be very unlikely, and for a large, heavy object such as a car, it would be very, very unlikely, but it would not be impossible. Thus, given enough time, it would be compulsory. If we waited long enough, we would find the car rolling down the other side of the hump. This phenomenon is called tunneling because it would be as if the car had passed under the hump through a tunnel. For an object as massive as an automobile, the probability that it will tunnel is so small that it would take an enormous amount of time, on average, for the car to appear spontaneously on the other side of the hump. To write a number big enough to express this amount of time would require so many digits that even if each digit were no bigger than a proton and they were solidly packed, the digits would more than fill the universe. However, exactly the same effect can allow an alpha particle, 2 protons and 2 neutrons, to tunnel out of a nucleus, or an electron to tunnel across a gap in a circuit. What I was imagining that day in 1972 is that although classical black holes have a fixed shape, quantum fluctuations can cause the shape of the horizon to jiggle. Normally, the shape of a non-spinning black hole is a perfect sphere, but a quantum fluctuation should be able to deform it briefly to a flattened or an elongated shape. Furthermore, every so often a fluctuation can be so large that the black hole will be deformed almost to a pair of smaller spheres connected by a thin neck. From there, it is easy for it to split. Heavy nuclei spontaneously split in this way, so why not a black hole? Classically, it cannot happen, just as the car cannot spontaneously hop over the hump. But is it absolutely forbidden? I could see no reason why it should be. Wait long enough, I reasoned, and the black hole will split into two smaller black holes. Now back to the West End Cafe. Nursing a beer, I waited for Feynman in the cafe for about half an hour. The more I thought about it, the more sense it seemed to make. The black hole could disintegrate by quantum tunneling, first into 2 pieces, then into 4, 8, and eventually a large number of microscopic components. In light of quantum mechanics, it made no sense to believe that black holes were permanent. Feynman entered the cafe just a minute or 2 early and came over to where I was sitting. I was in the mood to be a big shot, so I ordered 2 beers. Before I had a chance to pay, he pulled out his wallet and put down the required amount. I don't know whether he left a tip. I sipped my beer, but I noticed that Feynman's glass never left the table. I began by reviewing my argument and ended by saying that I thought the black hole ought to eventually disintegrate into tiny pieces. What could those tiny pieces be? Although it went unsaid, the only reasonable answer was elementary particles such as photons, electrons, and positrons. Feynman agreed that there was nothing to prevent this from happening, but he thought I had the wrong picture. I had visualized the black hole first splitting into more or less equal fragments. Each fragment would split in half until the fragments were microscopic. The problem was that a gigantic quantum fluctuation would be required for a large black hole to split in half. Feynman felt that there was a more plausible picture in which the horizon would split into a piece almost equal to the original horizon and a second microscopic piece that would fly away. As the process repeated, the large black hole would gradually shrink until there was nothing left. This sounded right. A tiny piece of the horizon breaking off seemed much more likely than the black hole splitting into 2 large fragments. The conversation lasted for about an hour. I don't recall saying goodbye, nor did we plan to pursue the idea. I had met the lion, and he hadn't disappointed me. Had we thought more about the problem, we might have realized that gravity would most likely pull the tiny fragments back down to the horizon. Some ejected fragments might collide with falling fragments. The region just above the horizon would be a complicated mess of colliding fragments that might be heated by the repeated collisions. We might even have realized that the region just above the horizon would be a seething mass of particles that formed a hot atmosphere. And we might have realized that this heated mass would behave like any heated object and radiate away its energy as heat radiation. But we didn't. Feynman went back to his partons, and I returned to the problem of what keeps quarks confined to the interior of protons. Now it is time to tell you exactly what information means. Information, entropy, and energy are 3 inseparable concepts that are the subject of the next chapter. Chapter 7. Energy and Entropy. Energy. Energy is a shapeshifter. Like mythical shapeshifters that could change from human to animal to plant to rock, energy also can change its form. Kinetic, potential, chemical, electrical, nuclear, and thermal heat are some of the many shapes that energy can take. It is constantly morphing from one form to another, but there is one constant. Energy is conserved. The sum total of all forms of energy never changes. Here are some examples of shapeshifting. Sisyphus is low on energy, so before pushing his boulder to the top of the hill for the umpteenth time, he stops to refresh himself with a meal of honey. When the boulder reaches the top, the condemned man watches while gravity rolls it back to the bottom for the umpteenth plus 1 time. Poor Sisyphus is doomed to eternally convert chemical energy, honey, to potential energy, and then to kinetic energy. But wait, what happens to the kinetic energy of the boulder when it rolls to rest at the bottom of the hill? It is converted to heat. A bit of heat flows into the atmosphere and into the ground. Even Sisyphus is heated by the effort. The Sisyphus cycle of energy conversion is as follows: chemical to potential to kinetic to thermal. Water flows over Niagara Falls and picks up speed. The flowing water, laden with kinetic energy, is directed into the mouth of a turbine where it spins the rotors. Electricity is produced and flows through wires into the grid. Can you chart the shape-shifting? Here it is. Potential to kinetic to electrical. In addition, some of the energy is uselessly converted to heat. The water that comes out of the turbine is warmer than the water that went in. Einstein proclaimed that mass is energy. What Einstein meant when he said E equals mc squared was that every object has some latent energy that can be released if somehow its mass can be changed. For example, a uranium nucleus will eventually break apart into a thorium nucleus and a helium nucleus. The thorium and helium will together have slightly less mass than the original uranium. That little bit of excess mass will morph into the kinetic energy of the thorium and helium nuclei, and also a few photons. When the atoms come to rest and the photons are absorbed, the excess energy becomes heat. Of all the usual forms of energy, heat is the most mysterious. What is it? Is it a substance like water, or is it something more ephemeral? Before the modern molecular theory of heat, early physicists and chemists thought that it was a substance and that it behaved like a fluid. They called it phlogiston and imagined that it flowed from hot objects to cool ones, cooling the hot and warming the cool. Indeed, we still speak of the flow of heat. But heat is not a new substance. It's a form of energy. Shrink yourself to the size of a molecule and look around at the hot water in a bathtub. You can see the molecules randomly moving and colliding in a bustling, chaotic dance. Let the water cool and look around again. The molecules move more slowly. Cool it to the freezing point and the molecules become stuck in a crystal of solid ice. But even in the ice, the molecules continue to vibrate. They cease moving, ignoring quantum zero-point motion, only when all the energy has been drained away. At that point, when the water is at minus 459.67 degrees Fahrenheit, or absolute zero, the temperature cannot be lowered any further. Every molecule is rigidly locked in place, in a perfect crystalline lattice, all confusion and chaotic motion stopped. The conservation of energy as it shifts shape from heat to other forms is sometimes called the first law of thermodynamics. Entropy. It would be a bad idea to park your BMW in the rainforest for 500 years. When you came back, you'd find a pile of rust. That's entropy increasing. If you left the rust pile for another 500 years, you could be pretty sure it wouldn't turn back into a working BMW. That, in short, is the second law of thermodynamics. Entropy increases. Everyone talks about entropy. Poets, philosophers, computer geeks. But what exactly is it? To answer this question, consider the difference between the BMW and the heap of rust more closely. Both are collections of about 10 to the 28th power atoms, mostly iron, and in the case of rust, also oxygen. Imagine that you took those atoms and threw them together randomly. What is the likelihood that they would come together to form a working automobile? It would take a good deal of expertise to say just how unlikely that would be, but I think we can all agree that it would be extremely unlikely. Obviously, it would be far more probable that you'd get a pile of rust than a brand new automobile, or even an old rusty one. If you took the atoms apart and threw them together again and again and again, you'd eventually get a car, but in the meantime you'd get a lot more rust piles. Why is that? What's so special about the car, or the rust pile? If you imagined all the possible ways that you could assemble the atoms, the overwhelming majority of the arrangements would look like rust heaps. A much smaller fraction would resemble an automobile, but even then, if you looked under the hood, you would most likely find a rust heap. An even tinier fraction of the arrangements would form a working automobile. The entropy of a car and the entropy of a rust heap have something to do with the number of arrangements that we would recognize as rust heaps versus the number that we would recognize as a car. If you shook up the atoms of a car, you would be much more likely to get a pile of rust because there are so many more rust pile arrangements than car arrangements. Here is another example. An ape banging away at a typewriter will almost always type gibberish. Very rarely will he type a grammatically correct sentence such as, "I want to arbitrate my hypotenuse with the semicolon." Even less frequently will he write a meaningful sentence such as, "King Canute had warts on his chin." What's more, If you take the letters of a meaningful sentence and shake them up like tiles in a Scrabble game, the result will almost always be gibberish. The reason? There are a lot more nonsensical ways to arrange 20 or 30 letters than there are meaningful ones. The English alphabet has 26 letters, but there are simpler systems of writing. Morse code is a very simple system, using only two symbols, dot and dash. Strictly speaking, there are three symbols, dot, dash, and space, but one could always replace the space with some special series of dots and dashes that is otherwise unlikely to occur. Anyway, ignoring the space, you could write the description of King Canute and his warts in Morse code, with 65 symbols in all. How many distinct Morse code messages could be made out of 65 dots and/or dashes? All you have to do is multiply 2 together 65 times to get 2 to the 65th power, which is about 10 billion billion. When information is coded in terms of two symbols, they could be dots and dashes, ones and zeros, or any other pair. The symbols are called bits. Thus, in Morse code, King Canute had warts on his chin is a 65-bit message. If you are going to read the rest of this book, it would be a good idea to memorize the definition of the technical term bit. Its meaning is not the same as when you say, "I'll take a bit of cream in my coffee." A bit is a single, irreducible unit of information, like the dots and dashes in Morse code. Why do we go to the trouble of reducing information to dots and dashes, or zeros and ones? Why not use sequences of 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, or even better, the letters of the alphabet? Messages would be a lot easier to read, and they would take up a lot less space. The point is that the alphabet, or the 10 ordinary numerals, is a human construct that we learn to recognize and store in our memories. But each letter or numeral already has a great deal of information. For example, in the intricate difference between the letters A and B, or the numbers 5 and 8. Telegraphers and computer scientists who rely only on the simplest mathematical rules prefer, in fact they are almost forced, to use the binary code of dots and dashes, or zeros and ones. Indeed, when Carl Sagan designed a system for sending messages to non-human civilizations living on distant solar systems, he used the binary code. Back to King Canute. How many of the 65-bit messages are coherent sentences? I really don't know, perhaps a few billion, but whatever the number is, it is an infinitesimal fraction of 2 to the 65th power. So it's almost certain that if you take the 65 bits, or the 27 letters of King Canute had warts on his chin, and scramble them, gibberish will be the result. Leaving out the spaces, here is what I got when I did it with Scrabble tiles. Hitkidjen Kwan Hitsurinesawachai. Suppose you only scramble the letters a little at a time. The sentence will gradually lose its coherence. King Canute had warts on his chin is still recognizable. So is Knig Canute had warts o his chin. But gradually the letters will become a meaningless jumble. There are so many more meaningless combinations that the trend toward gibberish is inescapable. Now I can give you a definition of entropy. Entropy is a measure of the number of arrangements that conform to some specific recognizable criterion. If the criterion is that there are 65 bits, then the number of arrangements is 2 to the 65th power. But entropy is not the number of arrangements, in this case 2 to the 65th power. It is just 65, the number of times you have to multiply 2 together to get the number of arrangements. The mathematical term for the number of times 2 must be multiplied together to get a given number is called its logarithm. Thus, 65 is the logarithm of 2 to the 65th power. Entropy is, therefore, the logarithm of the number of arrangements. Of the 2 to the 65th power possibilities, only a very small fraction are actually meaningful sentences. Let's guess that there are a billion. To make a billion, you have to multiply together about 30 factors of 2. In other words, a billion is about 2 to the 30th power, or, equivalently, 30 is the logarithm of a billion. It follows that the entropy of meaningful sentences is only about 30, a good deal less than 65. Meaningless jumbles of symbols clearly have more entropy than combinations that spell out coherent sentences. It's hardly surprising that entropy increases when you scramble the letters. Suppose that the BMW company improved its quality control to the point where every car that came off the assembly line was identical to every other. In other words, suppose there was one, and only one, atomic arrangement that would be accepted as a true BMW. What would its entropy be? The answer is 0. There would be no uncertainty whatever about any detail when a BMW rolled off the assembly line. Whenever one specifies a unique arrangement, there is no entropy at all. The second law of thermodynamics, which says that entropy increases, is just a way of saying that as time goes on, we tend to lose track of the details. Imagine that we put a tiny droplet of black ink into a tub of warm water. At first, we know precisely where the ink is located. The number of possible configurations of the ink is not too large. But as we watch the ink diffuse through the water, we begin to know less and less about the locations of the individual ink molecules. The number of arrangements that correspond to what we see, namely a uniform, slightly gray tub of water, has become enormous. We can wait and wait, but we won't see the ink rearrange into a concentrated drop. Entropy increases. That's the second law of thermodynamics. Things tend toward boring uniformity. Here is yet another example, a bathtub full of hot water. How much do we know about the water in the tub? Assume that it has been sitting in the tub long enough that there is no detectable motion. We can measure the amount of water in the tub, 50 gallons, and we can measure the temperature, 90 degrees Fahrenheit. But the tub is full of water molecules, and there are obviously a very great number of molecular arrangements that correspond to the given conditions, that is, 50 gallons of water at 90 degrees Fahrenheit. We could know a lot more if only we could measure every atom precisely. Entropy is a measure of how much information is hidden in the details. Details that for one reason or another are too hard to observe. Thus, entropy is hidden information. In most cases, the information is hidden because it concerns things that are too small to see and too numerous to keep track of. In the case of the bathwater, these things are the microscopic details of the water molecules, the location and motion of each of the billion individual water molecules in the tub. What happens to the entropy if the water is cooled until its temperature is absolute 0? If we remove every bit of energy from the water, the molecules will arrange themselves in a unique arrangement, the frozen lattice that forms a perfect crystal of ice. Even if the molecules are too small to see, if you are familiar with the properties of crystals, you can predict the position of every molecule. A perfect crystal, like a perfect BMW, has no entropy at all. How many bits can you stuff in a library? Ambiguity and subtle nuance in the use of language is often highly valued. Indeed, if words had perfectly precise meanings that could be programmed into a computer, language and literature would be impoverished. But precision in science requires a great degree of linguistic exactitude. The word information can mean many things. I think your information is wrong. For your information, Mars has 2 moons. I have a master's degree in information science. You can find the information in the Library of Congress. In each of these sentences, the word information is being used in a specific way. Only in the last sense of the word does it make sense to ask, where is the information located? Let's pursue this idea of location. If I told you that Grant is buried in Grant's tomb, we would no doubt agree that I have given you a piece of information. But where is that information? Is it in your head? In my head? Is it somehow too abstract to have a location? Is it diffused throughout the universe for anyone, anywhere to use? Here is one answer that is very concrete. The information is on the page, stored in the form of physical letters composed of carbon and other molecules. In this sense, information is a concrete thing, almost a substance. It is so concrete that the information in your book and in my book is different information. In your book, it says that Grant is buried in Grant's tomb. You may suspect that it says the same thing in my book, but you don't know for sure. Just maybe, my book says that Grant is buried in the Great Pyramid of Giza. In fact, neither book contains the information. The information that Grant is buried in Grant's tomb is in Grant's tomb. In the sense that physicists use the word, information is made of matter. When physicists use the word matter, they don't mean only things made of atoms. Other elementary particles such as photons, neutrinos, and gravitons also qualify as matter. And it is found somewhere. The information in this book is in a rectangular volume of space about 10 inches by 6 inches by 1 inch, that is, 10 times 6 times 1, or 60 cubic inches. These dimensions are a rough guess based on the size of the hardcover edition of my previous book, No doubt the actual dimensions of this audiobook are a bit different. How many bits of information are hidden between the covers of the book? In a line of print, there is room for about 70 characters, letters, punctuation marks, and spaces. At 37 lines per page and 350 pages, that's almost 1 million characters. My computer keyboard has about 100 symbols, including lowercase and uppercase letters, numbers, and punctuation marks. That means that the number of distinct messages that could be contained in this book is about 100 multiplied by itself 1 million times. In other words, 100 to the millionth power. That amount, a massive number, is roughly the same as multiplying 2 about 7 million times. The book contains about 7 million bits of information. In other words, if I had written the book in Morse code, it would have taken 7 million dots and dashes. Dividing that by the volume of the book, we find that there are about 120,000 bits per cubic inch. That's the information density in this volume of printed pages. I once read that the great library in Alexandria contained 1 trillion bits of information before it burned to the ground. Though not one of the official 7 wonders of the world, the library was nonetheless one of the greatest marvels of antiquity. Built during the reign of Ptolemy II, it is said to have contained a copy of every important document ever written, in the form of 500,000 parchment scrolls. No one knows who burned it down, but we can be sure that a lot of priceless information went up in smoke. Just how much? I'd guess that there were about 50 modern pages in an ancient scroll. If those pages were anything like the pages you were reading, a scroll was worth 1 million bits, give or take a few 100,000. At that rate, Ptolemy's library would have contained 500 billion. 1 trillion equals 10 to the 12th power bits. Close enough to what I read. The loss of that information is one of the great misfortunes that scholars of the ancient world have to live with today. But it could have been worse. What if every nook and cranny, every available cubic foot, had been filled with books like this one? I don't know exactly how big the great library was, but let's say 200 by 100 by 40 feet, or 800,000 cubic feet, the size of a good-sized public building today. That would be 1.4 billion cubic inches. With that knowledge, it's easy to estimate how many bits could be stuffed into the building. At 120,000 bits per cubic inch, the grand total is 1.7 times 10 to the 14th power bits. Stupendous. But why stop with books? If each book were shrunk to 1/10 its volume, 10 times as many bits could be crammed in. Transferring the contents to microfiche could allow for even more storage, and digitizing each book might allow for even more. Is there a fundamental physical limitation to the amount of space needed to contain a single bit? Must the physical size of a real bit of data be bigger than an atom, a nucleus, a quark? Can we subdivide space indefinitely and fill it with endless amounts of information? Or is there a limit? Not a practical, technological limit, but a consequence of a deep law of nature? The littlest bit. Smaller than an atom, smaller than a quark, smaller even than a neutrino, the single bit may be the most fundamental building block. Without any structure, the bit is just there, or not there. John Wheeler believed that all material objects are composed of bits of information, and he expressed the idea with this slogan, "It from bit." John imagined that a bit, being the most basic of all objects, is as small as the smallest possible size, that fundamental quantum of distance discovered by Max Planck more than a century ago. A rough picture that most physicists have in their minds is that space can be divided into tiny Planck-sized cells, similar to a three-dimensional checkerboard. A bit of information can be stored in each cell. The bit can be pictured as a very simple particle. Each cell may contain a particle or not. Another way to think of the cells is that they make up a huge three-dimensional tic-tac-toe game. According to Wheeler's it-from-bit philosophy, the physical conditions of the world at any given time can be represented by such a message. If we knew how to read the code, we would know exactly what was going on in that piece of space. For example, is it what we normally call empty space, a vacuum, or is it a piece of iron, or the interior of a nucleus? Since things in the world change with time, planets move, particles decay, people are born and die, the message in the O's and X's also must change. At one instant, the pattern might look one way, a little later, it might be rearranged. In this wheel or world of information, the laws of physics would consist of rules for how the configuration of bits is updated from instant to instant. Such rules, if correctly constructed, would allow waves of O's and X's to propagate across the lattice of cells and represent light waves. A large, solid lump of O's might disturb the distribution of X's and O's in its vicinity, and in this way, the gravitational field of a heavy mass might be represented. Now let's return to the question of how much information could be stuffed into the Alexandria Library. All we have to do is divide the volume of the library, 1.4 billion cubic inches, into Planck-sized cells. The answer is about 10 to the 109th power bits. That's a lot of bits, far more than the entire internet and all of the books, hard drives, and CDs in the world contain. Indeed, vastly more. To get some idea of how much information 10 to the 109th power bits is, let's imagine how many ordinary books it would take to store it. The answer is far more than we could possibly fit into the entire observable universe. The it-from-bit philosophy, describing a cellular world filled with Planck-sized bits of information, is an enticing one. It has influenced physicists on many levels. Richard Feynman was a great advocate of it. He spent a good deal of time building simplified worlds made of space-filling bits. But it's wrong. As we will see, Ptolemy would have been disappointed to learn that his great library could never have held more than a mere 10 to the 74th power bits. As it happens, that is about the number of bits that could be contained in a universe full of printed books. I can more or less picture what a million means. A cube, 1 meter on a side, contains a million gumdrops. But what about a billion? Or a trillion? It's harder to visualize the distinction, even though a trillion is 1,000 times bigger than a billion, and numbers like 10 to the 74th power and 10 to the 109th power are far too big to comprehend, except to say that 10 to the 109th power is a lot bigger than 10 to the 74th power. Indeed, 10 to the 74th power, the actual number of bits that could fit in the Alexandria Library, is an infinitesimal fraction of the 10 to the 109th power bits that we computed. Why is there such an enormous discrepancy? That is a story for a later chapter, but I will give you a hint here. Fear and paranoia among kings and princes is an all too common theme of history. I have no idea whether Ptolemy suffered from it, but let's imagine how he might have responded to a rumor that secret information was being hidden in his library by his enemies. He might have felt himself justified in passing a draconian law that forbade any hidden information. In the case of the Alexandria Library, Ptolemy's imaginary law would require every bit of information to be visible from outside the building. To satisfy the law, all of the information had to be written on the exterior walls of the library. The librarian was forbidden to hide a single bit in the interior. Hieroglyphs on the exterior walls allowed. Roman, Greek, or Arabic writing on the walls, allowed. But scrolls brought into the interior, forbidden. What a waste of space, but it was the law. Under these circumstances, what was the maximum number of bits that Ptolemy could expect to store in his library? To find the answer, Ptolemy had his servants carefully measure the external dimensions of the building and compute the area of the external walls and roof. Let's ignore the arches and the floor. They came up with 200 by 40 plus 200 by 40 plus 100 by 40 plus 100 by 40 plus 200 by 100, which equals 44,000 square feet. Notice that this time the unit is square feet rather than cubic feet. But the king wanted the area measured in Planck units rather than square feet. I'll do it for you. The number of bits that he could plaster on the walls and ceiling was about 10 to the 74th power. One of the most surprising and outlandish discoveries of modern physics is that in the real world, there is no need for Ptolemy's law. Nature already provides such a law, and even kings can't break it. It's one of the deepest and most profound laws of nature we have discovered. The maximum amount of information that can be stuffed into a region of space is equal to the area of the region, not the volume. This strange restriction on filling space with information is the subject of Chapter 18. Entropy and heat. Heat is the energy of random chaotic motion, and entropy is the amount of hidden microscopic information. Consider the tub of water, now cooled to the coldest possible temperature, absolute zero, at which point every molecule is locked into its precise location in an ice crystal. There is very little ambiguity in the location of each molecule. In fact, anyone who knows the theory of ice crystals could say exactly where each atom lies, even without a microscope. There is no hidden information. The energy, temperature, and entropy are all zero. Now, add a bit of heat by warming the ice. The molecules begin to jiggle, but only a bit. A small amount of information is lost. We lose track, if only a little, of the details. The number of configurations that we might mistakenly confuse with one another is larger than it was. Thus, a bit of heat raises the entropy, and it gets worse as more energy is added. The crystal approaches the melting point, and the molecules begin to slide right past each other. Keeping track of the details quickly becomes prohibitive. In other words, as energy increases, so does entropy. Energy and entropy are not the same thing. Energy takes many forms, but one of those forms, heat, is joined at the hip with entropy. More about the second law. The first law of thermodynamics is the law of energy conservation. You cannot create energy, you cannot destroy it. All you can do is change its form. The second law is even more discouraging. Ignorance always increases. Imagine a scene in which a diver plunges into a swimming pool from a springboard. Potential energy goes into kinetic energy, goes to heat. He quickly comes to rest, and the original potential energy is converted to a slight increase in the thermal energy, heat, of the water. With that slight increase, there is a slight increase in entropy. The diver would like to repeat the performance, but he's lazy and doesn't want to climb the ladder to the diving board again. He knows that energy can never disappear, so why not just wait until some of the heat in the pool gets converted back to potential energy, his potential energy? Nothing about the conservation of energy would prevent him from being shot up to the diving board while the pool cools a bit, the reverse of the dive. Not only would he wind up on the board, but the entropy of the pool would decrease, implying a surprising decrease in ignorance. Unfortunately, our wet friend finished only half his thermodynamics course, the first half. In the second half, he would have learned what we all know. Entropy always increases. Energy always degrades. The change of potential, kinetic, chemical, and other forms of energy into heat always favors more heat and less of those organized, non-chaotic forms of energy. This is the second law. The total entropy of the world always increases. It's for this reason that a car will screech to a halt when the brakes are applied, but applying the brakes to a stationary car will not get it moving. The random heat of the ground and the air cannot be turned into the more organized kinetic energy of a moving vehicle. It's also the reason that the heat in the sea cannot be tapped to solve the world's energy problems. On the whole, organized energy degrades to heat, not the other way around. Heat, entropy, information. What do these practical utilitarian concepts have to do with black holes and the foundations of physics? The answer is everything. In the next chapter, we will see that black holes are fundamentally reservoirs of hidden information. Indeed, they are the most densely packed information storage containers in nature, and that may be the best definition of a black hole. Let's find out how Jacob Bekenstein and Stephen Hawking came to realize this central fact. Chapter 8. Wheeler's Boys, or How Much Information Can You Stuff in a Black Hole? In 1972, while I was talking to Richard Feynman in the West End Cafe, a Princeton graduate student named Jacob Bekenstein was asking himself this question: what do heat, entropy, and information have to do with black holes? At that time, Princeton was the world's center for the study of gravitational physics. That may have had something to do with the fact that Einstein had lived there for more than 2 decades, though by 1972 he had been dead for 17 years. The Princeton professor who had inspired many brilliant young physicists to study gravity and think about black holes was John Archibald Wheeler, one of the great visionaries of modern physics. Among the many famous physicists who were profoundly influenced by Wheeler during this period were Charles Misner, Kip Thorne, Claudio Teitelbaum, and Jacob Bekenstein. Wheeler, who earlier had been Feynman's PhD advisor, was a disciple of Einstein. Like the great man himself, he believed that the key to the laws of nature lay in the theory of gravity. But unlike Einstein, Wheeler, who had worked with Niels Bohr, was also a believer in quantum mechanics. Thus, Princeton was a center of research, not only on gravity, but also on quantum gravity. At that time, the theory of gravity was a relatively unpopular backwater of theoretical physics. Elementary particle physicists were making giant strides in the reductionist march toward ever tinier structures. Atoms had long given way to nuclei, and nuclei to quarks. Neutrinos were finding their rightful role as equal partners with electrons, and new particles, such as the charmed quark, had been hypothesized and were within a year or two of experimental discovery. The radioactivity of nuclei was finally being mastered, and the standard model of elementary particles was about to be declared. Elementary particle physicists, myself included, thought they had better things to do than waste their time on gravity. There were exceptions, such as Steven Weinberg, but most considered the subject to be frivolous. In retrospect, this disdain for gravity was a very myopic view. Why was it that the aggressive leaders of physics, the bold frontiersmen of the subject, were so uncurious about gravity? The answer is that they could see no way that gravity could possibly have significance for the way elementary particles interact with one another. Imagine that we had a switch that allowed us to turn off the electrical force between an atomic nucleus and the electrons, thereby leaving only gravitational attraction to hold the electrons in orbit. What would happen to an atom when we flipped the switch? The atom would immediately expand, because the force that holds it together would have diminished. How big would a typical atom become? A good deal bigger than the entire observable universe. And what would happen if we left the electrical force switched on, but turned off gravity? The Earth would fly away from the Sun, but the change in an individual atom would be far too small to make any difference. Quantitatively, the gravitational force between two electrons in an atom is roughly 1,000,000 billion times weaker than the electrical forces. Such was the intellectual environment when John Wheeler boldly set out to explore the ocean of ignorance that separated the conventional world of elementary particles from Einstein's theory of gravity. Wheeler himself was a walking enigma. In appearance, he looked and sounded like a buttoned-down businessman. He could easily have fit into the boardrooms of the most conservative corporations in America. In fact, his politics were conservative. The Cold War was far from over, and John was a staunch anti-communist. And yet, throughout the 1960s and 1970s, in an age of unprecedented campus activism, he was deeply beloved by his students. Claudio Teitelbaum, who today is the most eminent Latin American physicist, was one of John's students. Claudio, the scion of a famous Chilean left-wing political family, was one of John's many disciples who later achieved fame. The family was politically allied with Salvador Allende. Claudio himself was a fearless, outspoken foe of the dictatorial Pinochet regime. But despite their political differences, John and Claudio have had an extraordinary friendship based on love and mutual respect for each other's opinions. The first time I met Wheeler was in 1961. I was an undergraduate at City College of New York, with a somewhat unorthodox academic record. One of my instructors, Harry Sudak, a cigar-chomping, cussing professor from the same Jewish left-wing working-class background that I came from, took me down to Princeton to meet him. The hope was that Wheeler would be impressed, and that I would be admitted as a graduate student, despite my lack of an undergraduate degree. At the time, I was working as a plumber in the South Bronx, and my mother thought I should dress properly for the meeting. To my mother, that meant that I should show solidarity with my social class and dress in my work clothes. These days, my plumber in Palo Alto dresses about the same way that I do when I lecture at Stanford University. But in 1961, my plumbing costume was the same as my father's and that of all his South Bronx plumber buddies: Lil Abner bib overalls, a blue flannel work shirt, and heavy steel-toed work shoes. I also sported a watch cap to keep the dirt and grime out of my hair. When Harry picked me up for the drive to Princeton, he did a double take. The big cigar fell from his mouth, and he told me to go back upstairs and change. He said that John Wheeler was not that kind of guy. When I walked into the great professor's office, I saw what Harry meant. The only way I can describe the man who greeted me is to say that he looked Republican. What the hell was I doing in this wasp's nest of a university? 2 hours later, I was completely enthralled. John was enthusiastically describing his vision of how space and time would become a wild, jittery, foamy world of quantum fluctuations when viewed through a tremendously powerful microscope. He told me that the most profound and exciting problem of physics was to unify Einstein's two great theories, general relativity and quantum mechanics. He explained that only at the Planck distance would elementary particles reveal their true nature, and it would be all about geometry, quantum geometry. To a young aspiring physicist, the stuffy businessman exterior had morphed into an idealistic visionary. I wanted more than anything to follow this man into battle. Was John Wheeler really as much of a conservative as he appeared? I don't really know. But he was certainly not a prudish moralizer. Once, while John and my wife Anne and I were having a drink in a Valparaiso cafe on the beach, he got up to take a walk, saying he wanted to check out the South American girls in their bikinis. At the time, he was in his late 80s. In any case, I never did get to be one of Wheeler's boys. Princeton did not admit me. So I went off to Cornell, where physics was far tamer. It would be many years before I felt the same thrill I had in 1961. Sometime around 1967, Wheeler became very interested in the gravitationally collapsed objects that Carl Schwarzschild had described in 1917. At that time, they were called black stars or dark stars. But that didn't capture the essence of the objects, the fact that they are deep holes in space whose gravitational attraction is irresistible. Wheeler began calling them black holes. At first, the name was blackballed by the preeminent American physics journal Physical Review. Today, the reason seems hilarious. The term black hole was deemed obscene. But John fought it through the editorial board, and black holes they became. Amusingly, John's next coinage was the saying, "Black holes have no hair." I don't know whether Physical Review was again outraged, but the terminology stuck. Wheeler wasn't trying to provoke the journal editors. Instead, he was making a very serious point about the properties of black hole horizons. What he meant by hair was observable features, perhaps bumps or other irregularities. Wheeler was pointing out that the horizon of a black hole was as smooth and featureless as the smoothest bald pate, actually much smoother. When a black hole formed, say by a star collapsing, the horizon very quickly settled down to a perfectly regular, featureless sphere. Apart from their mass and rotational speed, every black hole was exactly like every other. Or so it was thought. Jacob Bekenstein, an Israeli, is a small, quiet man, but his gentle, scholarly appearance belies his intellectual boldness. In 1972, he was one of Wheeler's graduate students interested in black holes, but he was not interested in these objects as astronomical bodies that might someday be seen through telescopes. Bekenstein's passion was the foundations of physics, the basic underlying principles, and he had a sense that black holes had something profound to say about the laws of nature. He was particularly interested in how black holes might fit together with the principles of quantum mechanics and thermodynamics that had so preoccupied Einstein. In fact, Bekenstein's style of doing physics was much like Einstein's. Both were masters of the thought experiment. With very little mathematics, but with a lot of deep thinking about the principles of physics and how they apply to imaginary, but possible, physical circumstances, both men were able to draw far-reaching conclusions that would profoundly affect the future of physics. Here is Bekenstein's question in a nutshell. Imagine yourself orbiting a black hole. In your possession is a container of hot gas, gas with a good deal of entropy. You throw the container of entropy into the black hole. According to the standard wisdom, the container would simply disappear behind the horizon. For all practical purposes, that entropy would completely vanish from the observable universe. According to the prevailing view, the featureless, bald horizon couldn't possibly hide any information, so it would seem that the entropy of the world had decreased, in contradiction with the second law of thermodynamics, which says that entropy never decreases. Could it be that easy to violate so deep a principle as the second law? Einstein would have been appalled. Bekenstein concluded that the second law is too deeply rooted in the rules of physics to be so easily violated. Instead, he made a radical new proposal. Black holes themselves must have entropy. He argued that when you count up all the entropy in the universe, the missing information in stars, interstellar gas, the atmosphere of the planets, and all the bathtubs of warm water, you must include a certain amount of entropy for each black hole. Furthermore, the bigger the black hole is, the bigger its entropy. With that idea, Bekenstein could rescue the second law. Einstein would no doubt have approved. Here is how Bekenstein thought about it. Entropy always goes together with energy. Entropy has to do with the number of arrangements of something, and that something, in all cases, has energy. Even the ink on a page is made of massive atoms, which, according to Einstein, have energy, because mass is a form of energy. One might say that entropy counts the possible ways of arranging bits of energy. When Bekenstein, in his imagination, tossed a container of hot gas into a black hole, he was adding to the black hole's energy. In turn, this meant an increase in the black hole's mass and size. If, as Bekenstein guessed, black holes have entropy, which increases with their mass, there was a chance of rescuing the second law. The entropy of the black hole would increase more than enough to compensate for what was lost. Before explaining how Bekenstein guessed the formula for black hole entropy, I will explain why it was such a shocking idea. So shocking that, according to Stephen Hawking, he initially dismissed it as nonsense. You can read all about his initial skepticism in his book, A Brief History of Time. Entropy counts alternative arrangements, but arrangements of what? If a black hole horizon is as featureless as the smoothest conceivable bald head, what is there to count? According to this logic, a black hole should have zero entropy. John Wheeler's claim that black holes have no hair seemed to directly contradict Jacob Bekenstein's theory. How to reconcile teacher and student? Let me give you an example that will help you understand. The print on a page decorated with various shades of gray is really composed of tiny black and white dots. Let's suppose we have 1,000,000 black dots and 1,000,000 white dots to work with. One possible pattern would be to divide the page in half, either vertically or horizontally. We can make one half black and the other half white. There are only 4 ways to do this. Left side white, right side black, left side black, right side white, top half black, bottom half white, top half white, bottom half black. We see a strong pattern and sharp distinctions, but only a very few arrangements. Strong patterns and sharp distinctions typically mean small entropy. But now let's go to the other extreme and randomly distribute the equal number of black and white pixels over the same square. What we see is a more or less uniform gray. If the pixels are really small, the gray will look extremely uniform. There is an enormous number of ways to rearrange the black and white dots that we would not notice without a magnifying glass. In this case, we see that large entropy often goes together with a uniform, bald appearance. The combination of apparent uniformity and large entropy indicates something important. It implies that the system, whatever it is, must be made of a very large number of microscopic objects that A, are too small to see, and B, can be arranged in many ways without changing the basic appearance of the system. How Bekenstein calculated the entropy of a black hole. Bekenstein's observation that black holes must have entropy, in other words, that despite their apparent baldness they hold hidden information, is one of those simple but profound observations that, at a stroke, change the course of physics. When I began to write books for a general audience, I was strongly advised to keep the equations down to only one, E equals mc squared. I was informed that for every additional equation that I included, I would sell 10,000 fewer books. Frankly, that goes against my experience. People like to be challenged. They just don't like to be bored. So after a good deal of soul-searching, I decided to take the risk. Bekenstein's argument is one of such extraordinary simplicity and beauty that I feel not to include it in this book would be a sad dumbing down of the material. However, I have taken pains to explain the results so that the less mathematically inclined reader can safely skip over the few simple equations without losing the essence. Bekenstein didn't directly ask how many bits could be hidden inside a black hole of a given size. Instead, he asked how the size of a black hole would change if a single bit of information was dropped into it. This is similar to asking how much the water in a bathtub will rise if a single drop of water is added. Even better, how much will the water rise if a single atom is added? That raised another question: how to add a single bit? Should Bekenstein throw in a single dot printed on a scrap of paper? Obviously not. That dot is composed of a huge number of atoms, and so is the paper. There is far more information in that dot than a single bit. The best strategy would be to throw in one elementary particle. Suppose, for example, that a single photon falls into a black hole. Even one photon can carry more than a single bit of information. In particular, there is a good deal of information in knowing exactly where the photon enters the horizon. Here, Bekenstein made clever use of Heisenberg's concept of uncertainty. He argued that the location of the photon should be as uncertain as possible, provided only that it gets into the black hole. The existence of such an uncertain photon would convey only a single bit of information, namely, it's there, somewhere in the black hole. Recall from Chapter 4 that the resolving power of a light beam is no better than its wavelength. Now, in this particular case, Bekenstein did not want to resolve a spot on the horizon. He wanted it to be as fuzzy as possible. The trick was to use a photon of such long wavelength that it would be spread out over the entire horizon. In other words, if the horizon has Schwarzschild radius r sub s, the photon should have about the same wavelength. Even longer wavelengths might seem like an option, but they would just bounce off the black hole without getting trapped. Bekenstein suspected that an extra bit added to the black hole would make it grow by a tiny increment, similar to the way that adding an extra rubber molecule to a balloon would increase its size. But calculating the growth required a few intermediate steps. Let me outline them first. 1. To begin with, we need to know how much the energy of the black hole increases when we add a single bit of information. That amount, of course, is the energy of the photon that carries the bit. So, determining the energy of the photon is the first step. 2. Next, we need to determine how much the mass of the black hole changes when the extra bit is added. To do this, we recall Einstein's most famous equation, E equals mc squared. But we read it backward. It tells us the change in mass in terms of the added energy. Once the change in mass is known, we can compute the change in the Schwarzschild radius using the same formula that Michel, Laplace, and Schwarzschild worked out. See Chapter 2. R sub s equals 2mg divided by c squared. Finally, we must determine the increase in the area of the horizon. For that, we need the formula for the area of a sphere. Area of horizon equals 4 pi r sub s squared. We begin with the energy of the one-bit photon. As I explained earlier, the photon should have a long enough wavelength that its location is uncertain within the black hole. That means the wavelength should be r sub s. According to Einstein, a photon of wavelength r sub s has an energy, E, given by the following formula. E equals hc divided by r sub s. In this formula, h is Planck's constant, and c is the speed of light. The implication is that dropping a single bit of information into the black hole will increase its energy by an amount hc divided by r sub s. The next step is to compute how much the mass of the black hole changes. To convert energy to mass, you have to divide by c squared, which means that the mass of the black hole will increase by an amount h divided by r sub s c. Change in mass equals h divided by r sub s c. Let's plug in some numbers to see how much a single bit would add to the mass of a solar mass black hole. Planck's constant, h, 6.6 times 10 to the negative 34th power. Schwarzschild radius of black hole r sub s, 3,000 meters, equals 2 miles. Speed of light, c, 3 times 10 to the 8th power. Newton's constant, g, 6.7 times 10 to the negative 11th power. Thus, one bit of information added to a solar mass black hole will add an astoundingly small amount of mass. Increase in mass equals 10 to the negative 45th power kilograms. But still, as they say, that ain't nothing. Let's proceed to step 3, using the connection between mass and radius to calculate the change in r sub s. In algebraic symbols, the answer is as follows. Increase in r sub s equals 2hg divided by r sub s c cubed. For the solar mass black hole, r sub s is about 3,000 meters. If we plug in all the numbers, we will find that the radius will increase by 10 to the negative 72nd power meters. This is not only vastly smaller than a proton, but it is also vastly smaller than the Planck length, 10 to the negative 35th power meters. With such a small change, you might wonder why we even bother to calculate it. But it would be a mistake to ignore it. The final step is figuring out how much the area of the horizon will change. For the solar mass black hole, the increase in the horizon area is about 10 to the negative 70th power square meters. That's very small, but again, that ain't nothing. And not only ain't it nothing, it's something very special. 10 to the negative 70th power square meters just happens to be 1 square Planck unit. Is that an accident? What would happen if we tried it for an Earth-mass black hole, a black hole as big as a cranberry, or a black hole 1,000,000,000 times more massive than the Sun? Try it out, either with numbers or with equations. Whatever the size of the original black hole, this is the rule. Adding 1 bit of information will increase the area of the horizon of any black hole by 1 Planck unit of area, or 1 square Planck unit. Somehow, hidden in the principles of quantum mechanics and the general theory of relativity, there is a mysterious connection between indivisible bits of information and Planck-sized bits of area. When I explained all of this to my pre-med physics class at Stanford, someone in the back of the room let out a long, low whistle, then said, "Cool." It is cool, but it's also profound and probably holds the key to the puzzle of quantum gravity. Now imagine building up the black hole bit by bit, just as you might fill a bathtub atom by atom. Each time you add a bit of information, the area of the horizon increases by 1 Planck unit. By the time the black hole is completed, the area of the horizon will be equal to the total number of bits of information hidden in the black hole. That was Bekenstein's great achievement, all summarized in this slogan: the entropy of a black hole measured in bits is proportional to the area of its horizon measured in Planck units. Or more succinctly, information equals area. It almost seems that the horizon is densely covered with incompressible bits of information, more or less the same way that a tabletop could be densely covered with coins. Adding an extra coin to the crowd would increase its area by the area of 1 coin. Bits, coins, it's the same principle. The only problem with this picture is that there are no coins at the horizon. If there were, Alice would have discovered them when she fell into the black hole. According to the general theory of relativity, to the freely falling Alice, the horizon is an invisible point of no return. The possibility that she will encounter anything like a table full of coins is in direct conflict with Einstein's equivalence principle. This tension, the apparent inconsistency between the horizon as a surface packed densely with material bits and the horizon as a mere point of no return, was the casus belli of the black hole war. Another point has puzzled physicists since Bekenstein's discovery. Why is the entropy proportional to the area of the horizon and not the volume of the interior of the black hole? It seems as if there is a lot of wasted space inside. In fact, a black hole sounds an awful lot like Ptolemy's library. We will return to that point in Chapter 18, where we will see that all the world is a hologram. Although Bekenstein had the right idea, black hole entropy is indeed proportional to area. His argument was not perfectly precise, and he knew it. He didn't say that entropy is equal to the area measured in Planck units. Because of a number of uncertainties in his calculation, all he could say was that the entropy of a black hole is about equal, or proportional, to the area. In physics, about is a pretty slippery word. Is it twice the area, or a quarter of the area? Bekenstein's arguments, though brilliant, were not powerful enough to fix the exact factor of proportionality. In the next chapter, we will see how Bekenstein's discovery of black hole entropy led Stephen Hawking to his greatest insight. Black holes not only have entropy, as Bekenstein correctly surmised, but they also have temperature. They are not the infinitely cold, dead objects that physicists had thought them to be. Black holes glow with an inner warmth, but in the end that warmth leads to their destruction. Chapter 9. Black Light. The winter wind is meanest in big cities. It funnels down long corridors between flat-faced buildings and whips around corners, mercilessly flailing unfortunate pedestrians. One very nasty day in 1974, I was out taking a long run through the icy streets of northern Manhattan, icicles of sweat hanging from my long hair. After 15 miles, I had reached exhaustion, but I was still a regrettable 2 miles from my warm office. Without my wallet, I didn't even have the necessary 20 cents to take the subway back. But luck was with me. As I stepped off the curb somewhere around Dyckman Street, a car pulled up next to me, and Age Peterson stuck his head out the window. Age was a delightful pixie of a Dane who had been Niels Bohr's assistant in Copenhagen before coming to the United States. He loved quantum mechanics and lived and breathed Bohr's philosophy. Once inside the car, Age asked if I was on my way to Dennis Sharma's lecture at the Belfer School. I wasn't. In fact, I didn't know anything about Sharma or his lecture. Instead, I was thinking about a hot bowl of soup in the university cafeteria. Aga had met Sharma in England and said that he was an enormously amusing Englishman from Cambridge University who could be counted on for lots of good jokes. Aga thought that the lecture had something to do with black holes, some work that Sharma's student had done and that had Cambridge all abuzz. I promised Aga that I would show up. The Yeshiva University cafeteria was not a place much to my liking. The food was not bad. The soup was kosher, that I couldn't have cared less about, and it was hot, that was important. But the conversation among the students irritated me. It was almost always about the law, not the federal law, or the state or city law, or the laws of science. Rather the hair-splitting minutiae of Talmudic law that animated the young yeshiva undergraduates. Would Pepsi be kosher if it were made in a factory that was built on a former pig farm? What if the ground was covered with plywood before the factory was built? That kind of thing. But the hot soup and cold weather encouraged me to dawdle and eavesdrop on some students at the next table. This time, the subject of the conversation was an item that even I cared about: toilet paper. The raging Talmudic debate was over the momentous issue of whether toilet paper rollers may be restocked during the Sabbath, or whether one must use the paper straight from an unmounted roll. From various passages in Rabbi Akiva's writings, one faction had surmised that the great man would have insisted on rigorous obedience to certain laws which forbade restocking the roller. The other faction believed that the incomparable Rambam had made very clear in the Guide for the Perplexed that certain necessary tasks were exempt from these Talmudic injunctions. Rambam is the nickname of Rabbi Moses ben Maimon, who is better known to the non-Jewish world as Maimonides. And logical analysis favored the view that toilet paper restocking was one of those tasks. After half an hour, the argument was still raging. Several new young rabbis-to-be had joined the fray with additional ingenious, almost mathematical arguments, and I finally tired of the debate. You may wonder what this has to do with the subject of this book, Black Holes. Only this. My dalliance in the cafeteria caused me to miss the first 40 minutes of Dennis Sharma's brilliant lecture. Cambridge University, where Sharma was professor of astronomy and cosmology, was one of 3 places, besides Princeton and Moscow. The Great Gravity Center in Moscow was led by the legendary Russian astrophysicist and cosmologist Yakov B. Zeldovich, where the brightest and the best were testing their intellects against the profound puzzles of gravity. And as at Princeton, its young intellectual warriors were led by a charismatic, inspirational leader. Sharma's boys were a stellar group of brilliant young physicists, including Brandon Carter, formulator of the anthropic principle in cosmology, Sir Martin Rees, the Astronomer Royal of Great Britain, who now occupies Sir Edmund Halley's chair, Halley of cometary fame, Philip Candelas, the current Rouse Ball Professor of Mathematics at Oxford, David Deutsch, one of the inventors of quantum computing, John Barrow, a distinguished Cambridge astronomer, and George Ellis, the well-known cosmologist. Oh, yes, and there was also Stephen Hawking, who now sits in Isaac Newton's chair at Cambridge. It was, in fact, Stephen's work that Dennis was reporting that frigid day in 1974, but at the time, the name Stephen Hawking meant nothing to me. By the time I arrived at Sharma's lecture, it was 2/3 over. I was immediately sorry that I hadn't gotten there earlier. For one thing, I was not looking forward to going out into the freezing sleet in my running outfit again. It had gotten dark and no doubt even colder by the time Dennis finished. But it was more than the fear of frostbite that made me wish that Sharma was just beginning. As Aga had said, Dennis was an enormously entertaining speaker. The jokes were indeed outstanding, but more to the point, I was fascinated by the single equation on the blackboard. Usually by the end of a theoretical physics lecture, the blackboard is filled with mathematical symbols. But Sharma was a man of few equations. When I arrived, the blackboard looked about like this. At the top there was a circle, with rays emanating from it, and underneath an equation, T equals hc cubed over 16 pi squared gmk. Within 5 minutes I had deciphered what the symbols represented. In fact, they were all standard notation for familiar quantities in physics. But I didn't know the context, what the formula described, although I could tell that it was either very deep or very silly. It had only the most fundamental constants of nature in it. Newton's constant, G, which governs the force of gravity, was in the denominator, an odd place to find it. C, the speed of light, indicated that the special theory of relativity was involved. Planck's constant, H, whispered quantum mechanics. And then there was K, Boltzmann's constant. It was the last that seemed so out of place. What the hell was it doing there? Boltzmann's constant has to do with heat and the microscopic origin of entropy. What were heat and entropy doing in a quantum gravity formula? And what about the number 16 and pi squared? These were the kind of mathematical numbers that appear in all sorts of equations. No hint there. M was familiar, and Sharma's words reinforced my impression of its meaning. M was mass. Within a couple of minutes, I could tell that it was the mass of a black hole. Okay, black holes, gravity, and relativity, that made sense, but adding quantum mechanics seemed odd. Black holes are enormously heavy as the stars that preceded them, but quantum mechanics is for small things, atoms, electrons, and photons. Why bring quantum mechanics into a discussion of something as heavy as a star? Most confusing, the left side of the equation represented temperature, T. The temperature of what? The last 15 or 20 minutes of Sharma's lecture were enough for me to put the pieces together. One of Dennis's students had discovered something very odd. Quantum mechanics gives black holes thermal property, heat, and along with heat comes temperature. The equation on the blackboard was a formula for the temperature of a black hole. How strange, I thought. What gave Sharma the daffy idea that a dead star, a star that had completely run out of fuel, would have a temperature other than absolute zero? Looking at the intriguing formula, I saw an interesting correlation. The temperature of a black hole would be inverse to its mass. The bigger the mass, the smaller the temperature. A huge astronomical black hole as large as a star would have a tiny temperature, much colder than any object in any laboratory on Earth. But the real surprise which made me sit up in my chair was that tiny black holes, if they existed, were extraordinarily hot. Hotter than anything we had ever imagined. Yet Sharma had an even bigger surprise. Black holes evaporate. Physicists till then had believed that black holes, like diamonds, were forever. Once formed, no mechanism known to physical science could destroy or eliminate a black hole. The black vacancy in space formed by a dead star would persist, infinitely cold, infinitely silent, for all eternity. But Sharma told us that, like a drop of water left out in the sun, little by little, black holes evaporate and eventually disappear. As he explained, electromagnetic heat radiation carries away the mass of a black hole. To explain why Dennis and his student thought this, I need to fill you in on some things about heat and heat radiation. I'll come back to black holes, but first, a digression. Heat and temperature. Heat and temperature are among the most familiar concepts in physics. We all have a built-in thermometer and a built-in thermostat. Evolution provided us with a hardwired sense of cold and warmth. Warmth is heat, and cold is its absence. But what exactly is this stuff called heat? What goes on in a bathtub of hot water that's absent when the bathwater gets cold? If you look carefully through a microscope at little tiny specks of dust or grains of pollen suspended in warm water, you will see the grains stagger around like drunken sailors. The hotter the water, the more agitated the grains appear. It was Albert Einstein who in 1905 first explained that this Brownian motion is caused by the grains being constantly bombarded by rapidly moving, energetic molecules. Water, like all other materials, is composed of molecules moving hither and thither, banging into one another, into the walls of the container, and into any foreign impurities. When that motion is random and chaotic, we call it heat. For ordinary objects, when you add energy in the form of heat, the result is an increase in the random kinetic energies of the molecules. Temperature is, of course, related to heat. When the zigzagging molecules hit your skin, they excite nerve endings, and you experience a sense of temperature. The larger the energy of the individual molecules, the more your nerve endings are affected, and the hotter you feel. Your skin is just one of the many types of thermometers that can sense and register the chaotic motion of molecules. So, roughly speaking, the temperature of an object is a measure of the energy of its individual molecules. When an object cools, energy is being drained away, and the molecules are slowing down. Eventually, as more and more energy is eliminated, the molecules reach the lowest possible energy state. If we could ignore quantum mechanics, this would happen when the molecular motion ceased altogether. At that point, there would be no more energy to drain away, and the object would be at absolute zero. The temperature cannot be lowered any further than that. Black holes are black bodies. Most objects reflect at least a little bit of light. The reason that red paint is red is that it reflects red light. More accurately, it reflects a certain combination of wavelengths that the eye and brain perceive as red. Similarly, blue paint reflects a combination that we perceive as blue. Snow is white because the surface of ice crystals reflects all the visible colors equally. The only difference between snow and a mirror-like sheet of ice is that the granular structure of the snow scatters the light in all directions and breaks up the reflected image into thousands of tiny fragments. But some surfaces reflect almost no light at all. Any light that falls on the sooty surface of a blackened pot is absorbed into the layer of soot, heating both the black exterior and eventually the iron itself. These are the objects that our brains perceive as black. The physicist's term for a totally light-absorbing object is black body. By the time Sharma lectured at my university in New York, physicists had long known that black holes are black bodies. Laplace and Michel had suspected it in the 18th century, and Schwarzschild's solution of Einstein's equations had proved it. Light, falling onto the horizon of a black hole, is completely absorbed. Black hole horizons are the blackest of the black. But what no one knew before Hawking's discovery was that black holes have a temperature. Before that, if you had asked a physicist, what is the temperature of a black hole, the initial response probably would have been, black holes don't have temperatures. You might have responded, nonsense, everything has a temperature. A little thought might then have provoked the answer, okay, a black hole has no heat, so it must be at absolute zero, the lowest possible temperature. In fact, before Hawking, all physicists would have claimed that black holes were indeed black bodies, but black bodies at absolute zero. Now, it's not correct to say that black bodies don't give off any light at all. Take a sooty pot and heat it to a few hundred degrees and it will glow red, even hotter, and it will glow orange, then yellow, and eventually it will have a bright bluish-white appearance. Curiously, according to the physicist's definition, the sun is a black body. How odd, you say. The sun is about as far from being black as anything you can imagine. Indeed, the sun's surface radiates plenty of light, but it reflects none. To a physicist, that makes it a black body. Cool the hot pot, and it will glow with invisible infrared radiation. Even the coldest objects radiate some electromagnetic radiation, as long as they are not at absolute zero. But the radiation emitted by black bodies is not reflected light. It is produced by vibrating or colliding atoms, and unlike reflected light, the color depends on the temperature of the body. What Dennis Sharma explained was remarkable, and seemed a bit crazy at the time. He said that black holes are black bodies, but they are not at absolute zero. Every black hole has a temperature that depends on its mass. The formula was on the blackboard. He told us one more thing, in some way the most surprising of all. Since a black hole has heat and temperature, it must radiate electromagnetic radiation, photons, in the same way that a hot black pot does. That means that it loses energy. According to Einstein's E equals mc squared, energy and mass are really the same thing, so if a black hole loses energy, it also loses mass. That brings us to the punchline of Sharma's story. The size of a black hole, the radius of its horizon, is directly proportional to its mass. If the mass decreases, it follows that the size of the black hole decreases. So as a black hole radiates energy, it shrinks, until it is no bigger than an elementary particle, and then it is gone. According to Sharma, black holes evaporate away like puddles on a summer day. Throughout the lecture, or at least the part I witnessed, Sharma made it very clear that he was not the source of these discoveries. It was, Stephen says this, and Stephen says that. But despite what Dennis said, my impression at the end of the lecture was that the unknown Stephen Hawking was just a lucky student who happened to be at the right place at the right time to hook up with Dennis's research project. It is conventional for a well-known physicist to generously mention the name of a bright student during a lecture. Whether the ideas were brilliant or crackpot, I naturally assumed that they originated with the more senior physicist. That evening, I was firmly disabused of this assumption. Age, a few other physics faculty members from Belfer, and I took Dennis to dinner at a fine Italian restaurant in Little Italy. Over the meal, Dennis told us all about his remarkable student. In fact, Stephen was not a student at all. When Dennis spoke of his student Hawking, he was speaking in the same way that the proud father of a Nobel Prize winner might speak of my boy. By 1974, Stephen was a rising star in the world of general relativity. He and Roger Penrose had made major contributions to the subject. It was my own ignorance that had led me to believe that Stephen was merely the student of a generous thesis advisor. Over Italian food and good wine, I heard the amazing, stranger-than-fiction tale of the young genius who had blossomed only after being diagnosed with a debilitating disease. As a bright but somewhat egotistical graduate student, Stephen contracted Lou Gehrig's disease. The progression of the disease had been rapid, and he was, at the time of the dinner, almost completely paralyzed. Though unable to write equations and barely able to communicate, Stephen was holding his medical nemesis at bay and at the same time exploding with brilliant ideas. The prognosis was grim. Lou Gehrig's disease is a brutal killer, and Stephen would, by all accounts, be dead in a couple of years. Meanwhile, he was having a ball, joyously, Sharma's word, revolutionizing physics. At that time, Dennis's description of Stephen's courage under adversity seemed an exaggeration. But after knowing Stephen for almost 25 years, I would say that it sounded just like him. Both Stephen and Sharma were unknown quantities to me, and I had no idea whether evaporating black holes were a tall tale, a wild fringe speculation, or genuine. It was possible that I had missed some important parts of the argument while being educated about Jewish toilet paper laws. More likely, Dennis had just reported Stephen's conclusion without providing any technical underpinning. After all, Sharma was not an expert on the advanced methods of quantum field theory that Hawking had used. As I said earlier, he was a man of few equations. In retrospect, it seems odd that I didn't connect Sharma's lecture with the brief conversation I'd had 2 years earlier with Richard Feynman at the West End Cafe. Feynman and I also were speculating about how black holes might eventually disintegrate. But many months would pass before I put the two together. Stephen's argument. By his own account, Stephen did not at first believe the strange conclusion that Jacob Bekenstein, the then unknown Princeton student, had come to. How could black holes have entropy? Entropy is associated with ignorance of hidden microscopic structure, such as our ignorance of the precise location of the water molecules in a bathtub of warm water. Einstein's theory of gravity and Schwarzschild's black hole solution have nothing to do with microscopic entities. Moreover, it seemed that there was nothing about a black hole to be ignorant of. Schwarzschild's solution of Einstein's equations was unique and precise. For each value of mass and angular momentum, there was one and only one black hole solution. That's what John Wheeler meant when he said black holes have no hair. By the usual logic, a unique configuration, recall the perfect BMW of Chapter 7, should have no entropy. Bekenstein's entropy made no sense to Hawking until he found his own way to think about it. The key for Hawking was temperature, not entropy. By itself, the existence of entropy doesn't imply that a system has temperature. Logically, it is possible to imagine systems that can be arranged in many ways without changing their energy, but this never happens in real-world situations. A third quantity, energy also comes into the equation. The connection between energy, entropy, and temperature goes back to the origin of thermodynamics in the early 19th century. Thermodynamics is the study of heat. Steam engines were the thing then, and the Frenchman Nicolas Leonard Sadi Carnot was what you might call a steam engineer. He was interested in a very practical question: how to use the heat contained in a given amount of steam to do useful work in the most efficient way, how to get the biggest bang for the buck. In this case, useful work might mean accelerating a locomotive, which would require converting heat energy into the kinetic energy of a large mass of iron. Heat energy means the disorganized, chaotic energy of random molecular motion. By contrast, the kinetic energy of a locomotive is organized into the simultaneous, synchronized motion of a huge number of molecules all moving together. So the problem was how to turn a given amount of disorganized energy into organized energy. The problem was that no one really understood exactly what organized and disorganized energy meant. Carnot was the first to define entropy as a measure of disorganization. My own introduction to entropy was as an undergraduate mechanical engineering student. Neither I nor any of the other students knew anything about the molecular theory of heat, and I would bet that the professor didn't either. The course, Mechanical Engineering 101, Thermodynamics for Mechanical Engineers, was so confusing that I, who was by far the best student in the class, couldn't make any sense of it. Worst of all was the concept of entropy. We were told that if you heat something a small amount, the change in thermal energy divided by the temperature is the change in entropy. Everyone copied it down, but no one understood what it meant. It was as incomprehensible to me as the change in the number of sausages divided by the onionization is called the Flugelweiss. Part of the problem was that I really didn't understand temperature. According to my professor, temperature is what you measure with a thermometer. Yes, I might have asked, but what is it? I am fairly sure the answer would have been, I told you, it's what you measure with a thermometer. Defining entropy in terms of temperature is putting the cart before the horse. Although it's true that we all have an innate sense of temperature, the more abstract concepts of energy and entropy are much more basic. The professor should have first explained that entropy is a measure of hidden information and is given in bits. Then he could have gone on to say, correctly, temperature is the increase in the energy of a system when you add 1 bit of entropy. Strictly speaking, it's the temperature, measured from absolute zero, times Boltzmann's constant. Boltzmann's constant is nothing but a conversion factor that physicists often set to 1 by choosing convenient units for temperature.